So, welcome everyone. This is going to be a course on principles and applications of NMR spectroscopy. I am Hanudatta Atreya from NMR Research Center in IISc Bangalore. I work primarily in the area of biomolecular NMR, looking at different structures of proteins and nucleic acids. In this course, we are going to basically introduce you to a very basic aspects of what is NMR spectroscopy, what are the principles involved, how NMR spectroscopy can be applied to different areas of chemistry and biology. So, I will start from the very basic applications of NMR spectroscopy. As you can see, NMR spectroscopy is a very unique spectroscopic tool. It has applications in a wide area of science and technology. For example, it is applicable in agriculture, in medicines. This is very popular application called magnetic resonance imaging, and that is where MRI is used. And we will see shortly in this course towards the end that MRI, magnetic resonance imaging, is essentially NMR. NMR spectroscopy is also used in different areas like NMR microscopy, food technology. In fact, testing many of the food products nowadays in many companies abroad is done by NMR spectroscopy. But the main focus, the major focus of this course will be on what is called structural biology and structural chemistry. These are two major applications which has now come up in last 20 years, and we will see how nicely NMR spectroscopy can be used in this area. Having said that, NMR spectroscopy is applicable in various fields, and therefore there are a lot of Nobel prizes which have gone given to different discoveries made in NMR, starting from the beginning of NMR, which is 1952. Nobel prize was given to Felix Bloch and Purcell, who actually independently and simultaneously discovered the phenomenon of NMR spectroscopy. Richard Ernst got Nobel prize in 1991. And Richard Ernst is a very common name in chemistry and physics. Everybody is familiar with what is called Fourier transform NMR, FT-NMR, which is the technique which is used routinely in chemistry. And Richard Ernst discovered and developed many of the two-dimensional NMR methods, which we will see during this course. Professor Kurt Wuthrich from ETH, that is Switzerland, he got was awarded Nobel Prize in 2002. And his main contribution was developing new methodologies for structure determination of biomolecules. So, this is where basically NMR took off from being a tool of chemists to being a tool of biologists, mainly structural biologists, and this was a phenomenal growth. It has seen a phenomenal growth after that, and we will look at how NMR can be used for structure determination of small biomolecules such as peptides and proteins in this course. And a major use of NMR, as I mentioned in the previous slide, is in the area where we can look at imaging. So, this is a Nobel Prize which was awarded in 2003 to Peters Mansfield and Paul Lutteber. They had done seminal contributions to MRI, and MRI basically involves imaging of the whole body of the human or animal, and actually capturing the anatomy of the human system. So, you can see the huge range of applications which NMR has, right from physics to looking at chemistry and biology, and looking at the imaging. So, why is NMR such a very unique tool? So, this is what we will see now in this next slide. It is a very unique spectroscopic tool among all the other techniques which you might be aware of. The first and foremost is that NMR spectroscopy is a non-invasive and a non-destructive method. What does this mean? This means that if you take a sample of your compound, of your molecule, and record NMR data on that, you get back the sample intact. Nothing happens to the sample, it is not destroyed, and therefore it is a very non-invasive, very nice non-invasive technique. In fact, in MRI the same thing applies, because the whole body imaging is done in a non-destructive and a non-invasive manner. So, NMR is unique among many other techniques in this respect. The next point is that NMR spectroscopy, you can actually study each and every atom in a given molecule. So, as we know, molecules are made up of atoms, and there are different types of atoms in a given molecule, like in a drug molecule or in a biomolecule, and each and every atom can be selectively, you can probe them or look at them in a very sensitive manner. And this is the major, the very good advantage of NMR spectroscopy compared to other techniques, wherein in other techniques you look at the whole molecule as such, you do not actually get a glimpse of each and every atom in the molecule, but that is where NMR helps to come in to help us in finding the structure. Another important point about NMR spectroscopy is that you can actually study the sample or the compound or molecule which you are studying in under different conditions of pH. You can change the temperature, you can change the solvent, you can change the pressure. So, you can actually play around with any conditions of your sample and keep monitoring the data or looking at the spectra at different under different conditions. So, this is a major plus point again of NMR, because being a non-destructive technique, as long as the sample is valid or is not degraded, you can use any different conditions and probe the data. NMR spectroscopy, again, and the next very important point is that it is a very quantitative technique. So, you can actually quantify the amount of sample present in your study. So, this is something which is again it differs from many other techniques. So, because we do not destroy the sample, it is a non-destructive method, you can actually preserve the quantification, you can measure what is the amount of the sample present, and this is very useful for many applications. For example, when we see what is called as metabolomics, where we look at the quantity of sample in a given mixture, you would like to know what is the different amounts, relative amounts present, and this is where NMR spectroscopy is very useful and again stands out as a unique among other techniques. We can study all different states of matter such as solids, liquids and gases, and this is again a very important point, because many of the samples, like we look at polymers, if you look at different materials, they are in solid form, you cannot make them in liquid form. So, you can use solid state NMR spectroscopy to study that. Liquids is again the solution state, which is what 90% or most of the people do for using when they use NMR spectroscopy. So, solution state NMR is the standard approach, and of course, in some very rare cases you can also look at gases, but our focus in this course will be mainly liquids, where we will focus on solution state, and a few example if will required we will look at also solid state NMR spectroscopy. So, NMR can be also used for studying dynamics, and this is a very nice technique, because in many in different methods such as X-ray crystallography, what happens is you look at this the sample in a solid form, you look in a crystal form, and therefore you have frozen the sample in time, and what you can get only the structural information. But in NMR, what you are doing is you are looking at the sample in a solution form. So, in a solution form, the sample is in its native state, it is a native state, and therefore it has all the properties what you would expect in a real scenario, and therefore dynamics is one important property of a molecule. Most of the molecules in solution are very dynamic, they are never static as we see in pictures. So, therefore, the understanding dynamics is a very important part of understanding the whole function of the molecule, and this is where NMR spectroscopy stands out, and it helps us to look at dynamics at various time scales. You can go from as short as picoseconds to go as a few seconds. So, you can see there is a wide time scales of dynamic processes that can be studied by NMR. So, we will also look at this in this course. So, before we go on to the details of the course, I would like to suggest some books which you can actually refer to during this course. There is a very nice book called NMR Spectroscopy Explained by Neil Jacobson, and some of them are available online and you can have a look at them. James Skiller's book, which is Understanding NMR Spectroscopy, is the most popular book today among students, and this is something which is very nice, can be looked at. If you are interested in biological systems, which we will go to focus a little bit in this course, this book by Professor Chari and Govil is a very important book. So, while all these books are going to be used in some way or the other, we will cover all the details. So, these books will serve as mainly as a reference materials or for more deeper insight if you would like to have in the course. So, let us then begin with this course. So, before we start, NMR spectroscopy, as the word stands out, it is a spectroscopy technique. So, it is like one of the other many other spectroscopic techniques. So, we need to first understand what is spectroscopy in general, what does spectroscopy mean, what do we actually do in a spectroscopy. So, let us start from basic concepts in spectroscopy first, and then before we move on to NMR. So, when we talk about spectroscopy, spectroscopy involves the study of interaction of radiation with matter. So, when we say radiation, it is basically we are referring to what is called electromagnetic radiation, and this is light. So, like for example, sunlight consists of electromagnetic radiation of different wavelengths. So, you can see here there is this picture of a wave which is schematic drawing, and it shows that there are two components of a electromagnetic wave. One is called the electric field, that the blue color, and the other is the red color, and the other is the magnetic field, and these two fields are oriented perpendicular to each other. So, this is the standard picture of a wave, electromagnetic wave, and you can see there is what characterizes the wave is the wavelength, that is the number of waves which are present per meter or per second. So, when we talk about number of waves per second, we talk about what is called frequency. So, frequency is how many waves are travelling per second, and wavelength is the length of the wave. So, these are basically two properties which we will be very much using throughout our course, because this is a basic aspect of a spectroscopy. So, essentially what happens in spectroscopy is you take this kind of a electromagnetic field or a radiation or a wave, and you shine it on a sample. So, let us say that this what you are seeing in the center is, let us say, a sample. So, we call it as matter, or you can call it as your molecule or compound. So, when you shine light on this molecule, now the molecule starts responding, will respond to the incoming light. So, this incoming light we write it as this h mu, this is a photon. Right. So, one photon of energy is energy of one photon is h into mu, where h is the what is called as Planck's constant, and mu is the frequency of the wave. So, whenever there is a electromagnetic wave, its energy is given by h mu. So, this energy h mu is now is shown on the sample, and the sample then responds to this wave. So, it can do several things. Number one, it can absorb that wave, it can absorb that energy into the system, or it can simply scatter that energy, it just reflect the energy, or it just does not do anything and the wave simply passes through. So, when it simply passes through, that means the matter or the sample is transparent, it is invisible to the light. But when it absorbs, then it absorbs the energy, and part of it is absorbed, part of it is radiated back or transmitted out, or part of it is scattered. So, now what is that makes a matter or a compound absorb the energy or react to the energy? So, if you for this, we have to little bit go into what is called quantum mechanics or in physics. So, we say that if the matter at a microscopic, at an atomic level, does not have a continuum of energy levels. So, it has what is called discrete energy levels. That means, any sample will have, any compound will have a discrete energy level, and this is called quantized system. So, we have a quantized energy levels, and now the energy which is shown upon this matter sample will only be absorbed by the matter if the energy matches the difference as shown here, difference between the two energy level. Let us say that we have this is a very hypothetical system. Let us say we have what is called a ground state, and we have what is called an excited state. So, this is basically different energy levels in a matter, in the sample or in the compound molecule. So, the energy which we are supplying, there is h mu, if it matches this gap between the ground state and excited state, then this energy is absorbed by the sample and taken up by the molecules go from the ground energy level to an excited energy level. So, this is a qualitative way of explaining. For the deeper understanding, I would suggest to also go look at the different books which I refer to. But in a qualitative manner, one can understand that when you shine a light on this matter, the matter which has different energy levels in its molecule, the molecules will absorb that energies if there is a difference in the energy level matches the energy which we are supplying. So, this is basically the general idea of a spectroscopy, in spectroscopy, that you shine light on the matter either absorbs, reflects or transmits the light, and based on that you can find out what is happening in what is the nature of this matter. So, the nature of the matter is hidden in a way, in the way it responds to light. So, based on the response to the light which is shown on a matter, we can figure out what type of matter, what is the inside of this system consist of, and we can also look at different types of properties such as the structure of the molecule, the dynamics of the molecule, the vibrations, rotations and so on. So, there are different spectroscopic techniques. If you go to the next, we will go to the next slide. Here we see that depending on the property which you want to study, for example, let us say you are looking at the dynamics of the molecule or rotation of the molecules or vibrations, you can see there are different energies involved. So, that means based on what type of energy I apply to the sample, the different properties of the sample will respond to that kind of a spectrum, to that light. So, this is called the electromagnetic spectrum, where you can see the whole spectrum is now divided into different regions based on the frequency. So, remember frequency is measured in hertz. So, we are going to use this hertz units throughout the course. So, if you start from the lowest frequency, that is the lowest longest wavelength, remember wavelength and frequency are inversely related. So, if you go to the longest wavelength or the shortest lowest frequency, we use that word radio waves. So, this region is called radio waves. Then the next little higher energy is called microwave, and here the microwave energy, if you supply it to the sample or molecule, the rotation of the molecules are affected or respond to this particular range of frequency, and this is called microwave spectroscopy. Then the next energy is infrared, which is responded, which depends on the vibrations of the molecules. The vibrations in the molecule respond to infrared radiation, which is if it is applied to the sample. Then comes the electronic transitions, that means the electrons in the molecule respond to these energies, which is called ultraviolet, visible and ultraviolet. And visible is essentially, as a visible word means, it is essentially you can see, and this is the range of frequency. Ultraviolet is in the higher energy, and then as you go further, the very high energy rays, electromagnetic radiations, they are called X-ray, and X-ray is where X-ray radiations are used for different applications, and one of the very famous application is X-ray crystallography, where we look at structures of molecules, and further down higher energy is gamma rays. So, this is the different energy ranges which to which the molecules can respond depending on its property, depending on its composition or constitution and structure. So, NMR spectroscopy will focus on this lowest energy, that is radio waves. So, the whole of NMR spectroscopy technique is focused on this particular region and the radio waves. So, we can see what is the basic technique, what is the basic apparatus or what setup in any spectroscopic in general. As remember, NMR spectroscopy is also a spectroscopic technique. So, many of the things are indeed common with other spectroscopic technique, but the details will vary. But generally what you need is a source. So, you have a source of radiation, and this is what you shine on the sample. So, this is a sample, this is just a very schematic qualitative figure. So, you take the radiation which you put it on the sample, and the sample will absorb the radiation or transmit, and whatever is transmitted is detected by physically a detector, which is electronic component, and then you analyze it, and finally what is displayed is what is called a spectrum. The spectrum is essentially a plot of frequencies which are of the light which are absorbed by this radiation. So, the radiation basically is a broad source, can be a broad source of radiation, and different portions of the radiation can be is absorbed or transmitted by the sample, and that is what we record and display. So, for in terms of the perspective of NMR spectroscopy, this source will basically be a radio wave source, a source of radio waves, as we saw that NMR relies on radio frequency. So, now let us go to NMR spectroscopy, having understood what general spectroscopy means. So, let us go back to this picture where we see that there is a what is called a matter, in other words it is a sample or a molecule or a compound. So, you see every molecule, as we know from our basic chemistry and physics, there is made up of atoms. So, every molecule consists of atom. Now, if you look at atom more closely, atom consists of nucleus, which is at the center of the atom, and it is surrounded by a electron cloud or electrons. Now, if you zoom into this nucleus, you will see nucleus is made up of protons and neutrons, and we use the word nucleons, which for both protons and neutrons. Now, neutrons and protons have two properties associated with them, which we will use in NMR. One of the properties is called charge. So, all of us know that protons are positively charged and neutrons have charge 0, they are neutral. But what is one more important property they have is known as spin. So, spin is essentially an abstract quantity, it is a quantum mechanical quantity. So, although it is not literally that they are spinning, but we can always associate all the properties of motion with this quantity called spin. So, I would suggest that in the back of your mind you keep in mind that it is not literally rotation of a spin which is of a nucleus which is going on, but at the same time we associate a property called spin which will be very useful. So, the spin of a proton and neutron are same, they are fermions, and we use the word half h cross. This h is a Planck's constant, and half h cross h bar we use, that is h upon 2 pi. So, both protons and neutrons have spin, but the charge is only for proton and neutron does not have a charge. But if you see now, the overall nucleus has a positive charge, and that is again a well known thing, because the neutrons are positively, nucleus is positively charged and electrons are negative. So, so this whole positively charged nucleus now has a spin associated with it, because the protons and neutrons inside the nucleus have spins along with them. So, now what happens is that the protons and neutrons now start pairing up with each other. So, this is what happens, that suppose I have one proton and one neutron, they can pair up with each other such that one proton will have a positive half and the other nucleon will have a negative half, and they cancel each other. So, pairing essentially cancels out the nucleus, the spin of the particles. So, that means the nucleus, after pairing protons and neutrons together, you can say that the total nucleus has a net spin value. The net spin value is the value which you arrive at after pairing up all the protons and neutrons. So, this net spin can have any value, as we will see shortly. The net spin value can be determined based on the number of protons and neutrons, or basically based on the atomic mass and atomic number. But what is important is that the whole NMR the whole technique of spectroscopy, NMR spectroscopy, relies on the nucleus having a net spin value which is not 0. That means, if all the protons and neutrons pair with each other exactly, then the total spin value of the nucleus will become 0, because the positive spin will cancel with the negative spin of the nucleons, and therefore, if the net total spin is 0, then NMR cannot be carried out on that particular molecule. So, the atom. So, that means this atom or element should have what is called a non-zero spin. It cannot have a 0 spin. If it is 0, then it cannot be studied by NMR. So, we will see shortly what are the conditions which are important for getting a spin not equal to 0, total spin of a nucleus, or equal to half integer or integer. So, this concept that a nucleus is it is possible to study a nucleus by NMR or element, we use the word NMR active. So, we will say this particular NMR is a nucleus is NMR active, or this particular nucleus is not active. So, we will say NMR inactive. So, you can see so let us look at how one can actually qualitatively determine whether a particular nucleus can be studied by NMR or cannot be studied. So, you can see at this table here, it shows how we can estimate. So, let us say on this column here is atomic mass. So, you can have any atom having an even atomic mass, or it can be odd atomic mass. Similarly, an atomic number of that atom can be either even or odd, depending on the number of protons. So, number of protons will decide whether the atomic number is even or odd, and the total number of atoms, that is total number of nucleons, that is protons plus neutrons, determine whether the atomic mass is even or odd. So, this is a very standard basic concept which we learn in chemistry and physics. So, let us say we take a particular nucleus carbon 12, it has 6 protons and 6 neutrons. So, therefore, it is even atomic number and even atomic mass, and therefore, the spin of this is 0. That means, the total all the protons and neutrons pair with each other, and the total net value of the spin for that nucleus is equal to 0. So, therefore, we cannot study 12C by NMR. Similarly, oxygen 16 has 8 protons and 8 neutrons. So, it belongs to this even category, and therefore, it cannot be studied by NMR. Now, let us look at an example where you have odd atomic number and even atomic mass. So, this is the case where example deuteron, this is an isotope of hydrogen, and there is the nitrogen 14. So, if you look at this, they have 7 protons, nitrogen 14 has 7 protons, 7 neutrons. So, it has total even atomic mass, but atomic number is odd. So, such kind of a element atom or a nuclei will have what is called integral value of spins, means the spin will be the integer multiples of 1 and so on. Okay. Now, let us look at the third case where you have even atomic number and odd atomic mass, and such examples for that could be is 13C, oxygen 17. So, 13C is a very popular nuclei for NMR spectroscopy. So, here if you see we have 6 protons, that is even atomic number, but we have odd atomic mass. So, this therefore, the spin of this is half integer, and it could be half, 3 by 2, 5 by 2 and so on. That is for oxygen 17 it is 5 by 2, and for carbon 13 it is half. So, there are various rules by which you can determine the exact value of the spin, but the general qualitatively how we can get the idea is based on this table. Now, the last case is essentially odd combination. For example, this is a very most popular nucleus is proton. Of course, there is no neutrons for hydrogen atom, so it is called proton. So, it has one proton, and in the nucleus is therefore odd atomic number, also odd atomic weight mass, and that is why it is spin half integer. Very another important nucleus for NMR is N15, which has 7 protons and 8 neutrons. So, it makes this as an odd combination, and its spin value is half. So, therefore, these are basically the different conditions by which we can study the different NMR properties, and we will be focusing on this. So, in this manner you can actually extend this idea to the entire periodic table, although it is not very clear each of these numbers here, but the idea, the take home from this slide is that the many elements in the whole of periodic table which can be studied by NMR spectroscopy, because they have non-zero spin. Okay. So, either the compound the element itself can be studied in the natural abundance, or its isotope which will be less abundant. So, abundance is something which we will be very much referring to again and again in this course. The abundance basically means in a given natural state what is the percentage of a given isotope which is present in that molecule. For example, carbon 12 is naturally abundant 99%, that means 99% of the atoms in a molecule containing carbon is carbon 12, 1% is carbon 13. So, for us NMR, as far as NMR is concerned, only that 1% which is present contributes to the signal, the remaining 99% is not is just blind or transparent to NMR because it has spin 0. So, 1% is abundance. So, you can see the sensitivity is low, because only out of 100 atoms carbon, 1 carbon atom will be C13. So, similarly the abundance and nuclei will vary, and based on that the sensitivity is determined. So, as we go on we will look at the different reason or properties. So, sensitivity, how does it depend on the atom and nucleus, other properties and so on. So, from this onwards we will take up in the next class how actually we can look at the spin value, and then how does NMR spectroscopy depend on this particular spin, and how we take it forward. Thank you.